Right now we're going to take a look at this paper, Geometry, Logical Arguments, Rules of Logic. We're going to show you how to write Venn diagrams that relate to things, and this is going to be a review of all the different things that we've done in this unit. So the first thing that we're going to talk about is the law of detachment. Sometimes this is called the direct rule. So again, we have the definition in words. It says if P is true, then Q is true. P is true, therefore Q is true. So whenever we write symbols in this column here, we're going to translate. So the first line here, it says if P is true, then Q is true. So remember, that's if P, then Q. And then we just have P is true for the next line, which I'll do in green. P. And then we have this word therefore. So remember, the symbol for therefore are the three dots that make a triangle. Q is true, so there's Q. So that's just translating our words into symbols. As far as our picture goes, our Venn diagram, remember the hypothesis always goes inside of the conclusion Q. And since P is true, that means I'm somewhere in this first circle, somewhere in P. And this is valid. Anytime we have if P then Q is true, then P, therefore Q, it's always valid. Again, it's a law. It's the law of detachment. So if I play, then I win. So this is P, then Q. And then we have I play, which is P, therefore Q, which is I win. So if I wanted to draw this as a diagram, I would have play on the inside and win on the outside. Because remember, the conclusion goes on the outside, and I'm told that I play. So our next name that we have here, this is the law of contrapositive. This is the indirect argument. So we should be getting used to writing it in symbols. So the first line, if P is true, then Q is true. So just as before, if P, then Q. So we have something different. Not Q is true. So that's going to be not Q. So remember, the tilde means not. And then the last thing I have is therefore not P is true. So therefore not P is true. So if I want to draw this, again I have P on the inside, Q on the outside, so the conclusion is always outside of the hypothesis P. So I have not Q is true. So not Q is true means I'm outside of Q. I'm outside of the big circle. So this is always going to be valid. In our 2-2 notes, we said that whenever we have a true conditional, we'll have a true contrapositive. So to fill this in, if I play, then I win. I don't win. So right here I have P, then Q. I have not Q, therefore not P. Not P is I don't play. So if I'm going to draw this same thing again, remember I still have play on the inside, wins on the outside, but where I am, I say that I don't win. So I'm outside the two circles. Moving on, the next one is the law of syllogism. Sometimes this is called the chain rule. So we have if P is true, then Q is true. So if I do this in symbols, if P, then Q. The next line says, if Q is true, then R is true. So if Q, then R. Then we have P is true, so it's just P. And lastly, we have therefore. Again, therefore are the three dots. If P is true, then R is true. So P, then R. So to draw this one, we have P on the inside, Q further out, and then we have a third circle, which is R. So what we have is P is true. So that's what I had in blue. P is true, so that means I'm inside the first circle, which means I'm inside Q and I'm inside R. This is valid. The law of syllogism, again, it's another law. It says, if I play, then I win. So this is P, then Q. If I win, I am happy. That's Q, then R. I play, there's P. Therefore, I guess we shouldn't say, therefore, if we play, I know I am happy. So drawing this Venn diagram, we have play on the inside, that's P, win, and then we have happy all the way on the outside. So I'm told I play. So that means I'm inside the play circle. So we have a couple more. We have the converse error next. If you ever have any questions on what's going on, hopefully it's making sense as we're going on with all the different symbols. So the converse error says if P is true, then Q is true. So P, then Q. It then tells me Q is true. Therefore, P is true. So let's take a look at this. I still have P on the inside and Q on the outside. But now I'm told Q is true. So if Q is true, it could be anywhere. It can be where Q doesn't touch P, or it could be where Q touches P. So this is invalid. I'm not necessarily inside of the P circle. So this is a common mistake people make, where they're given the converse is true and they want to assume the hypothesis is true. That's not true. So if I take a look at this, it says if I play, then I win. So if P, then Q. So then we have I win. That's Q. The converse error, what a lot of people would want to say is, therefore I play. But this is invalid. So we would have play on the inside still, and on the outside we would have win. And as you can see, we might win something that we didn't play. So that's kind of a hard situation to come up with, but if you think about different McDonald's ads, they say if you play the Monopoly game, for example, you don't need to play to win. So that would be an example of a converse error. We also have an inverse error. So the inverse error says if P is true, then Q is true. Then it tells us not P is true. therefore not Q is true. So let's take a look at what this looks like. So again, we have the same starting point, P on the inside, Q on the outside, and we're told not P is true. Well, not P could be this first X, it could be this second X, it could be either Q or not Q. We don't know. So this is an invalid conclusion. Sometimes it works, sometimes it doesn't, just like the converse error. So an example of how people would screw this up would say, if I play, then I win. So we still have if P, then Q. I don't play, so we say not P. Therefore, a lot of people would say I don't win. And this is invalid. And to give you an example of where it's invalid, let's draw our Venn diagram again. So we have play, and we have win. So an example of where we don't play could be right here. It's outside of the play circle, but it's inside the win circle. So that's not always true. That's an error, the inverse error. Let's go over some other examples to see how these things work in practice. Let's take a look at the second page. We're still on the rules of logic here. It says, if I have $80, I will buy that dress. So remember, $80 goes on the inside. That's my hypothesis P. The conclusion is, I will buy that dress, so Q. So I don't have $80. So if I don't have $80, that means I'm either in this box or in the buy dress still, or I'm outside of both. So I don't have $80. So what this is not P, right? Therefore, I won't buy the dress. So we don't know if that's true. It looks like I went a little bit out of order. The symbols are what I should have done next. So if P, then Q, not P, therefore not Q. And we know from our Venn diagram that this is an error. This is the inverse error. And it's not valid. So it's an inverse error because we might not have $80 and we still might buy the dress. So hopefully the picture makes sense. Let's keep going. Let's try the next one. If I go to Best Buy, we'll call that P, I will buy a VCR. Q. I didn't buy VCR. That looks similar to Q, but it's not Q. So I didn't makes it not. Therefore, I did not go to Best Buy. So then I have not P. So the symbols are if P, then Q, not Q, therefore not P. So let's draw what the diagram looks like. We have Best Buy down here, that's our hypothesis. And then on the outside we have VCR. So not Q says I didn't buy the VCR, so that means I'm outside of the VCR circle, which means I didn't go to Best Buy. This is a valid argument. I can't ever go to Best Buy while not buying the VCR. And this is a rule. This rule was called the law of contrapositive. So if you're unsure of the law of contrapositive, just go back to the prior page and you'll see it's the same argument. So let's try the next one. If I ride the bus, then, if I ride the bus, I will get home at 2:30. So we have P and Q. So if P, then Q. I got home at 2:30. So that's Q. Therefore, I rode the bus. Therefore, P. So again, the hypothesis goes on the inside. You ride the bus home at 2:30. So we say I got home at 2:30. So if I get home at 2:30, that means I may or may not have ridden the bus. This is saying I always rode the bus, so that means it's an invalid conclusion. And this error is the converse error. It's the converse error because we may or may not have ridden the bus. We're not given enough information to determine anything. So I'm going to try two more. The next one is if a pig can fly, we'll call that P, then it has wings, Q. If a pig has wings, that's still Q, right? It has wings, a pig has wings, they're the same thing. Then it is strange, R. Therefore, if a pig can fly, P, then it is strange, R. So if P, then Q. If Q, then R. We have therefore, if P, then R. So whenever I would draw this out, I would have pig flying, wings, and then all the way on the outside it would be strange. That's what it looks like with the Venn diagram. So our conclusion is, therefore, if a pig can fly, so I'm inside this first circle, then it is strange. Well, yeah, it has to be strange. All the pigs flying are in the realm of strange, so this is valid. And this was called the law of syllogism.